Yeah, thank you very much. It's very exciting to be able to talk at this interesting conference. So I'm a postdoc here at the IOA, and I'll take us to the very old heart of the Milky Way. So this is a very nice map of stars from the Gaia mission of the Milky Way. It's around 2 billion stars that have been mapped here. So we can learn about them through various ways, like the dynamics or the chemistry. So one thing we found is that most of the stars in the Milky Way are reasonably metal-rich. So this is the sun in this metallicity scale is at 0. You have metal-poor stars, they have 1/10 of the metallicity of the sun. And these stars are mostly in the disk and the bulge of the Milky Way. But we can go to lower metallicities. So we can get a very extremely low metallicity. So this is 100th or 1,000th of the metallicity of the sun. And this is the realm of the galactic halo. So these are the metal-poor stars, and they're the witnesses of early galaxy formation. But we can go even more metal-poor. And this is the official nomenclature we use. It's ultra, hyper, mega metal-poor stars. And these are the descendants, we think, of the very first stars. So they have a very, very low iron abundance. They may have been enriched by just one supernova event from the first stars or a few of them. And their chemical abundances can teach us about, for example, the masses and rotation rates of the first stars. So we're interested in metal-poor stars for these two reasons: to study early galaxy formation and to locally get us back to the first stars that are no longer around. So what we find with our galaxy formation models and simulations is that the oldest stars should be very centrally concentrated. So this is a slice through a Milky Way-like simulation, which is color-coded by the fraction of very metal-poor stars that was born before a redshift of 7. And we can see that there's some in the outer regions of the halo, but this is very strong overdensity in the inner 3-4 kiloparsec. So metallicity is a good indicator of age, but it also depends on the environment. And these very inner regions is where we get the very first core of where the Milky Way started to form. But if we take observations of stars in the inner regions, most of them are going to be metal-rich and formed later. So these are mostly disky stars. They're in this range of -1 to slightly supersolar metallicities. So if you want to find these very metal-poor stars, you need to do more than just randomly target stars in the inner regions. You need an efficient way of finding these really old stars. And one additional complication is that there's lots of dust in our sight line. Of course, we are inside the Milky Way. If we're trying to look towards the center, we have to look through the disk, through the dust. And this is another region that classical searchers for metal-poor stars have, for a long time, avoided this very interesting region. So how do we find the metal-poor stars in the inner galaxy, these very old tracers? So one way is accidentally in large surveys. So there were a few in that figure that I showed before. You can look at variability, for example, Araliris stars, but one of the most efficient ways of doing this is using photometry, and especially metallicity-sensitive photometry. So you can use a combination of infrared photometry that's sensitive to metallicity, but what has been used a lot recently is narrowband photometry, and specifically in this very blue wavelength range, we have two very strong calcium lines, the calcium H and K lines. So if you build a filter like, for example, the SkyMapper V filter or the Pristine Calcium HK filter that are very narrow in this region, they'll be sensitive to the metallicity, because as the strength of these lines changes, you get a different absorption in this filter. And if you combine it with broadband photometry, you can make a beautiful color-color diagram where the metal-poor stars here in blue separate very nicely from the more metal-rich stars. So you can create photometric metallicities, but then also select the most metal-poor candidates for spectroscopic follow-up to get a large sample of these stars. And then also now you can use the large data set from Gaia. It has very low resolution spectra, spectrophotometry, and you can also get good metallicity estimates from that. And it's going to be all sky, but it's just going to be bright stars. So a project I want to highlight that I've been leading over the past few years is the Pristine Inner Galaxy Survey, or PIGS, where we're looking at the very center using this narrowband pristine calcium H and K filter. So in yellow, you can see the main pristine survey where we're looking at the galactic halo, typically the most metal-poor component. And then in pink, the very central footprint that we have to look for this really old heart of the Milky Way. So it's been going quite well. We've published quite a few papers on this component in various different topics, and I'll highlight mostly one of them. So to get from the photometry to get a spectroscopic sample, we've used the AAT with 2DF to follow up a bunch of these stars, resulting in 13,000 stars, of which 2,000 are very metal poor. So this is just the histogram of metallicity distributions compared to what you might get in random surveys. So we can use this sample. For the first time, we have really a large enough sample to look at these stars as a population. So first, let's look at the kinematics of these stars. How do they move? So a few years ago, the first PIGS paper, we found that metal-poor stars rotate slower than the bulk of the galactic bulge, which is not really surprising. So this is the galactic longitude. The center, galactic center is here, and the kind of projected radial velocity. So the points are from metal-poor stars in PIGS, and the lines are metal-rich stars, mostly the bulk of the stars. So you can see that the rotation is slower. So this is just using the radial velocities, but now with Gaia, we have the proper motions, we can derive distances, so you can get the full orbital properties of these stars. When you do that, you can look at various different things. So one of them is the azimuthal velocity, so the velocity around the galactic center. So two things. On the left, the middle panel, you can see the distribution of these velocities for the most metal-poor stars. And it's not centered at 0. So it means there's around a 40 kilometers per second rotation in this very old population. And then as you go to slightly higher metallicities, but this is still very metal-poor for the inner regions, it looks like there might be two different components in the velocity. One that is rotating around 70, 80 kilometers per second, and then one much broader component in the velocities. So what about the spatial distribution of metal-poor stars? It's a bit more difficult to do with PIGS because of our footprint and some other limitations, but this is where Gaia comes in. So this is a map of metal-poor stars based on the Gaia XP spectra. We can clearly see in the center this high overdensity of metal-poor stars. What in Rick's 2022 they call it the poor old heart of the Milky Way. So here, this is roughly the inner few degrees. And then if you look, again, back to PIGS at the orbital properties, we can look at the median apocenter, so how far out do these stars go on their orbits. And we find that the very metal-poor stars, most of them stay within around 5 kiloparsec, even more strongly peaked towards a closer center. And that means that not a lot of this population would come out to the solar neighborhood around 8 kiloparsec. So if you want to study this population, you really have to go and find it in the center. So then, what might we be looking at here? So we know that there's this central concentration of old stars in the Milky Way, slightly rotating. And this is the kind of more speculative part of the talk. So one, we can see, again, back to the velocities, there might be two different components. One more cold and faster rotating, and one broader and also more metal poor. And we think that maybe this first one could be connected to a proto-galactic component. So before the Milky Way had a disk, this kind of the kind of populations you might see at high redshift, where you just have a chaotic formation of the early Milky Way. And this is just a figure from someone looking at this in simulations. You can make a population that's initially not rotating, but it can gain some rotation over time, maybe through interactions with the disk or the bar. Or there could also be some initial angular momentum just from the build-up phase of the Milky Way. And this population would be very centrally concentrated. And then the more puffy population, potentially it was accreted at a later time, and therefore couldn't go as deep into the potential well of the Milky Way, or accreted from smaller systems. So smaller systems have lower metallicity, the mass-metallicity relationship, so there would be a more metal poor component, and if you have more systems, they're going to be less likely to have some net rotation, they're going to be fluffier as well. So this should leave traces in the chemistry of these stars. As we've just been talking about, the chemistry really tells us about where stars were born. So what do we know so far? So this is not just from PIGS, this is just kind of now an overview of what we know about the inner galaxy in chemistry. So overall, the very metal poor stars, they actually look quite similar to halo stars further out, overall, if you compare one-on-one. But there might be some trends that we need to look into a bit more. At intermediate low metallicity, so -1, -2, so 1/10 to 100th of the solar metallicity, we find that there's potentially signs that larger building blocks contribute to this component of the early Milky Way. We have faster chemical evolution rather than a small ultra-faint dwarf galaxies, for example. And as well, a large in situ component. So kind of the main building block of the Milky Way is where the chemical evolution went the fastest. And then also, as Keith mentioned earlier, that the fraction of globular cluster stars, at least from their chemistry, seems to be higher in the inner galaxy. So these are stars in the field, not associated with any particular globular cluster, but indicating that probably a large number of disrupted globular cluster contributes to this ancient inner galaxy population. So some challenges that we're facing is that samples are relatively small. This is just from a few different works. If you go below metallicity of -1.5 or so, and they're all analyzed differently. So it's difficult to compare them to each other, and then also to other regions of the Milky Way. So I'm very excited about FORMOS. FORMOS is a multi-object spectroscopic instrument. We'll be starting in a year or so, and it will be observing in the southern hemisphere, and which is perfect for targeting the galactic bulge. So it's going to target extragalactic, galactic projects, and among other things, there'll be a survey of metal poor stars. So I'm providing targets from the PIGS photometric catalog, because even in such a large survey, if you target randomly, there's not going to be that many of these metal poor stars. So we're inputting around 20,000, 30,000 of these stars, and then we'll get abundances for them. So specifically, this project is in low resolution. We're already going to get a bunch of different abundances, and then there'll be other projects as well. So then to wrap up, what do we know about the ancient heart of the Milky Way? Well, there's this central, slowly rotating concentration of old stars in our galaxy, and PIGS has really contributed to showing this population to us. So what is it made of? It's probably a combination of in situ stars, very old in situ stars, accretion events, disrupted globular clusters, and then with FORMOS, especially the Formidable, which is the disk bulge surveys, will provide completely different eyes on this ancient component. Thanks.
Thank you, Anke.